Hello guys, welcome to this session. Here in this session, we are going to discuss some problems of IIT JEE. These are subjective problems, okay, which has been asked in the previous year exams. As you can see, it is IIT 1990. The problem is the topic we have picked up today is electrochemistry, right? So here in this session, we are going to discuss some problems which has been asked in JEE exam of electrochemistry. As you can see, the first problem is calculate the electricity that would be required to reduce 12.3 gram of nitrobenzene to aniline if the current efficiency for the process is 50%. Okay, so current efficiency is 50%. If the potential drop across the cell is this, how much energy will be consumed? Okay, potential drop is given 3, right? It means that 3 is the we can say it is the EMF, right? It is the EMF of the cell. So energy consumed is what? It is nothing but the work done, correct? The energy which has been exchanged is nothing but the work done by the cell, or which happens, or the change in energy because of the flow of electrons, correct? So to solve this question, first of all, you should know one prior information you should have, that is how that nitrobenzene converts into aniline. This information you should have. Okay, so now you see this, the conversion of nitrobenzene into aniline. This reaction actually you should know. Okay, if you do not know this reaction, okay, you cannot do this question, this to this. Okay, so electricity that we require to reduce this gram of nitrobenzene to aniline. Now we all know what is nitrobenzene. It is C6H5. It is C6H5NO2, right? And it says to reduce nitrobenzene into aniline. And aniline is what? Aniline is C6H5NH2. This is what the reaction we have, right? But in this process, this takes place when this consumes hydrogen. That is a reduction reaction. It forms this, and H2O also goes out in this reaction. So if you balance this reaction, this reacts with 3 moles of this and forms 2 H2O, right? So you see here, we have okay, we have the mole ratio is 1:3 in this. Mole ratio is 1:3. If you find out the number of moles of C6H5NO2, which is the nitrobenzene here, this would be equals to the given mass 12.3 divided by the given mass divided by the molecular mass of nitrobenzene, which is 123 gram only. If you calculate this, you'll get 123 gram is the molecular mass of nitrobenzene. So 1 mole we have here, right? So 1 mole of this requires 3 mole of hydrogen for this reaction, first of all, correct? Oh, sorry, it is 0.1. I missed this, 0.1. So 1 mole requires 3. So 0.1 mole requires 0.3 mole of H2 for this reaction. Correct? 0.3 mole is required. Now the amount of charge required to liberate 0.3 mole of hydrogen. Okay, how this 0.3 mole of hydrogen liberates into this, right? So for this reaction, the charge required for this process will be charge required for this reaction will be The amount of H plus that you get here, 3 into 2, 6. So we'll write 2 into 96500, and we have 0.3 mole. So 0.3. 0.3. This is the amount of charge required. Okay. So when you solve this, you will get approximately 57900 coulomb. Okay, this is a charge required for this reaction to proceed. Right? So if you take this, it means you are taking the current efficiency, it says it is 50%. Right? It means when we have 100% efficiency, right, then the charge required is this for this reaction. But here what we say, the efficiency is only 50%. It means we must have to supply the double charge of it so that the process takes place, right? So for this reaction, since the current efficiency is 50%, so the actual value of charge will be what? Will be twice of this, 2 into 57900 coulomb, which is around 800.511. This coulomb of charge, if passes through, then this reaction is possible. Okay, 0.3 mole of hydrogen is consumed into this. Okay, now we have this is the charge, right? And we know, so this is what charge Q, right? This is the actual value of Q, and the potential difference is given, that is this thing, 3 volts. E cell is given is 3 volt, right? So the energy consumed is nothing but the change in delta G, or we can write energy consumed not change in delta G, but we can write the work done actually. So work done is nothing but Q into E cell is equals to 115800 into 3, right? So that will be approximately 34707400 joule of energy gets consumed here. Okay. So two things, current efficiency, if it is given, so depending upon the percentage, will have the charge required. If the current efficiency is not 100%, then actual charge will be more, right? We should have the charge so that with that efficiency also the reaction is possible. For this reaction, we require this much of charge, 57900 coulomb, right? So this much of charge you have to provide, okay? But current efficiency, it says 50%. That's if you provide this, then 50% of this only the actual charge is using up over here, right? So our reaction, that reaction is not possible in that case. In the desired result, we won't get, right? To allow this charge to pass through, we must have to provide the charge double of it. So we have to provide this much of charge so that effectively this coulomb of charge passes through this. And this E cell is this, energy consumed is Q into E cell. Okay, hope you understood this. Answer is this 3474. Okay, you can copy this down. Okay, now I see the next reaction. Next question is, next question is this. You can pause the video and then you can start solving it, okay? If you want to try on your own, okay? Okay. So in this question, you see the standard reduction potential of Cu2 plus to Cu and Ag plus to Ag electrode are given. Okay, construct a galvanic cell using these electrodes, right? Using these electrodes so that its standard EMF is positive. For what concentration of Ag plus will the EMF of the cell at this temperature would be 0, and if the concentration of Cu2, okay, fine. So basically, it's a very basic question based on a Nernst equation, correct? We can solve this question easily. First of all, the standard reduction potential is given. So E naught value of Ag plus to Ag is given 0.337 volt. E naught value for Cu2 plus to Cu, it is 0.337 volt. Okay, this I have written it by mistake. Ag is there, so Ag is 0.799. Okay, 0.799. This is given. Now, which one has more reduction potential? If you see, Cu2 plus to Cu and Ag plus to Ag, right? So if you write down the two half reaction here, you see what we get. Ag plus Ag plus to Ag plus one electron, you'll get Ag, and so this is what, this is a reduction, correct? So if you compare the reduction potential here, right, Ag has more standard reduction potential. Hence, when we have these two electrodes in combination, so this behaves as cathode. The one which has more reduction potential behaves as cathode, and the other one behaves as anode. Okay, cathode and anode. So this is the reaction of cathode, and the anode reaction is this. Cu solid gives Cu2 plus aqueous plus 2 electrons. This is solid, this is aqueous. Okay. Now, when you write down this equation, you have to multiply this by 2 so that the 2 electron gets cancelled. And the cell reaction is Cu solid plus 2 Ag plus gives 2 Ag plus Cu2 plus. Okay, it is aqueous, it is solid, and it is aqueous. This is the reaction we have. Now, when you apply Nernst equation into this, E cell is equals to E naught cell minus 0.0591 by N log of concentration of Cu2 plus by concentration of Ag plus square. Okay. Now, what is given the other set of data you see? The first of all, for this cell, the E naught value, E naught cell is equals to, we can write E cathode minus E anode. So cathode is Ag, so 0.799 minus 0.337. Okay, 0.799 minus 0.337. So that would be 0.462 volt. This is the E naught cell. And it is given here At what concentration, you see, at what concentration Ag plus will be, the EMF of the cell will be 0 if the concentration is this, right? So E cell also given for the question. E cell is 0 and concentration of Cu2 plus is given, that is 0.0. Now when you substitute all these value here in our equation, you'll get this as 0 is equals to 0.462 minus 0.0591 by 2 log of, we need to find out the concentration of Ag plus. So Cu2 plus is 0.01 divided by Ag plus square. Right? Now you can solve this equation. And you'll get the Ag plus concentration as 1.52 into 10 to the power minus 9. So this is the answer for this question. Okay. Okay. Third question. A current of 1.70 ampere is passed through 300 ml of 0.160 molar solution of zinc sulfate for 230 seconds. So I'll write down the data first here. That is given. The data given is I is equals to 1.70 ampere, volume of the solution is given, that is 300 ml, and for this solution the concentration is given molarity, and that will be 0.16 molar. Solution is zinc sulfate, ZnSO4, for 230 seconds. T is equals to, will take 230 seconds. Okay, current efficiency is given 90%. Okay, current efficiency is 90%. Means whatever the current we are passing through, 90% is only it is using. Okay, calculate the molarity of Zn2 plus iron after the decomposition of iron, decomposition of zinc, assuming the volume of the solution to remain constant during electrolysis. Now, this is a very good question. What happens if you allow the current to pass through? Then there will be a reaction, right? There will be a redox reaction. Zn plus 2, it gets reduced and deposited as Zn solid on the cathode electrode, right? On the cathode. So in that way, the concentration of Zn2 plus in the solution changes, right? Concentration changes, and hence molarity also changes. So hence we need to find out the molarity when deposition of zinc takes place. Okay. Okay. So if you know the amount of Zn plus 2 present in the solution after this decomposition, then we can find out the a molarity, because it is already mentioned in the question that the volume is not changing. So volume is given. You don't have to do anything with volume. Right? So volume is given. Just we need to know the concentration of Zn plus 2, right? Or the number of moles of Zn plus 2 in the solution when deposition of zinc takes place. Okay. Okay. So first of all, what we do here, you see, we know the mass deposited is equals to right. Mass is m is equals to zit zit. Okay. Z is what? Z is electrochemical equivalent. Okay. So further we can write this as Z is equals to E by 96500. Further, what is E? Number of equivalents. Okay. So E is what? Mass divided by equivalent mass. So E is the equivalent mass. So M by E is what? M by E is equals to IT by 96500. One more thing here, you see, it says 90% of the current efficiency, right? So the charge that passes through, charge is equals to, we have 1.70 current, but 90% of this, 90 by 100. So this is the actual current passes through. For how long? For 230 seconds. So charge that passes through from this, when you solve this, you'll get approximately 315, 1.9 coulomb, sorry. This is the charge we get. We can also take 352. Okay. This mass we can write, see, this mass we can write number of moles into molecular mass. You see, this expression is what? M by E, try to understand. M by E, we can write E is the equivalent mass, or suppose mass you have. So mass, what we can write? Moles into molecular mass, or zinc metal hai, so we can also write atomic mass divided by E. So molecular mass by E or atomic mass by V is N factor. So moles into N factor. Or we can also write number of equivalents. So basically M by E becomes moles into, because you see mass and this is equivalent mass. So mass divided by equivalent mass is what? Directly you can write number of equivalents. This way also you can do. Mass by equivalent mass is the number of equivalents is IT by 96500. So 1 by 96500 into the value of IT is 351.9 coulomb. And number of equivalents further we can write moles into n factor. N factor is 2 because we have Zn plus 2. So 351.9 divided by 2 into 96500. This is the number of moles of zinc which deposited onto the electrode. Okay, deposited onto the electrode, and this value is 0.000182. Okay, I am doing this with the help of calculator. Okay, but this is, you see, this is the question of 1991 subjective question, right? So in this kind of questions there were some calculation, complex calculation, but you won't get this kind of calculation in these exams, right? Nowadays whatever exams they are taking, they won't get such complicated calculations. Okay, so don't worry with that. But yes, concept you must understand. What is the concept we have? So this is the number of moles of Zn plus 2 get deposited, right? So what is the concentration? Because we need to find out the molarity. So the new molarity is what? Is the initial one. The initial one is this minus the change, the decrease in molarity, right? The decrease in molarity is this only minus of this moles is equals to how many, what is the molarity corresponding to this mole? 182 mole divided by volume is 300 because there is no change into this, into 1000 liter it is. This is the solution. So now when you solve this expression, you'll get approximately 0.0.152 molar. When you solve this, so this is the answer for this question. Okay, so this was the third question. The next one you see, okay, the zinc granules are added in excess to 500 ml of 1 molar nickel. Added in excess to 500 ml of 1 molar nickel nitrate solution at 25 degrees Celsius until the equilibrium is reached. If the standard reduction potential of zinc and nickel is given, find out the concentration of Ni2 plus solution at equilibrium, right? So we know first of all at equilibrium what happens? At equilibrium, delta G is 0, right? So the first thing that we know at equilibrium, delta G is 0 and hence E cell is equals to 0. And we can write E naught cell is equals to 2.303 RT log Kc, equilibrium constant. Okay. So now you see E naught cell we can find out. Obviously you see zinc and nickel both are getting reduced. So reduction potential is given minus 0.75 and 0 minus 0.04. So which one is more? Nickel is more, right? So nickel will go under reduction because the nickel reduction potential is more than to that of hydrogen. So what we can write, E naught of Ni2 plus to Ni is greater than E naught of Zn2 plus to Zn. Hence, this will go under reduction and this will go under oxidation, right? Hence, we have cathode of nickel rod and anode of zinc, right? So E naught cell, further we can calculate the E naught cell is equals to E naught of cathode, right? Both are reduction potential minus E naught of anode. So E naught of cathode is what? For nickel, it is minus 0.24 plus 0.75. Now, when you solve this, you'll get 5 minus 4 is 1, 7 minus 2, 5, 0 point this. This is the E naught cell we have, 0.5. Now, when you substitute this here, we'll get Kc. So log of Kc is equals to 0.51 divided by 2.303 RT is nothing but 0.0591 divided by n. N is nothing but 2, right? So this becomes 0.51 into 2 divided by 0.0591. So when you solve this, you'll get Kc is equals to 1.78 into 10 to the power 17. This is what the value of equilibrium constant we get. Okay. Now we have equilibrium constant, so we can find out the concentration of Ni2 plus at equilibrium. Okay. So what is the reaction we have? The reaction is Zn solid plus Ni2 plus converts into Zn2 plus Ni solid. So Kc is equals to, we'll take only ion, So Zn2 plus divided by this. Concentration. Okay, so if it is 1, 0, so 1 minus x, we can write x by 1 minus x. This we can solve x. This we can solve x by substituting the value of Kc, and x will be around 1. Okay, so you can find out x from this, and then you can find out 1 minus x. So 1 minus x will be approximately the nickel, and I see actually what happens here. This is the reaction, right? So initially, if it is 1, it is 0. Or you don't have to do anything over here. Kc is nothing but the concentration of Zn plus 2 by Ni2 plus. We need to find out the concentration of Ni2 plus ion in solution at equilibrium. In solution at equilibrium. So when the equilibrium is achieved, we'll get Kc as this. If it is 1 initially, so it is given excess of 1 molar. So 1 it is given. This is 1, this is 0. And then it becomes 1 minus x, and this is x. So this is x by 1 minus x. You can find out x from this by substituting the value of Kc, and then we can find out the concentration of Ni2 plus, which is 1 minus x, and it is coming out to be around 5.6 into 10 to the power minus 18 molar. Okay. We try to understand here. If you substitute Kc is equals to, here if you substitute Kc is equals to Zn2 plus by Ni2 plus, this Ni2 plus, we cannot take 1 molar here. Why we cannot take 1 molar? But because the condition is this, we have nickel nitrate solution, and in this we are mixing zinc granules into this, right? So when there is only nickel nitrate, then the concentration is 1 molar. When you mix this up, zinc granules into this, then there will be redox reaction, decomposition, deposition, and the other reactions takes place. So the concentration of nickel changes into this nickel nitrate solution. That concentration changes. Hence, we cannot take 1 molar nickel nitrate solution there, right? Means in the Kc expression, we cannot take the concentration of nickel as 1, right? That's why we have written this Kc expression separately. Okay, usually what mistake we do, that we substitute here Kc is equals to Zn plus 2 by Ni2 plus. And that Ni2 plus, we take it as 1, and then we solve this. That is not the case here. Keep that in mind, okay? Good question. Okay, next question you see. Okay, the question is, an aqueous solution of sodium chloride on electrolysis gives H2 gas, Cl2 gas, and NaOH according to the reaction. And the reaction is given 2Cl minus plus H2O gives 2OH minus H2 plus Cl. Okay, a direct current of 25 ampere with a current efficiency 62% is passed through 20 liter of NaCl solution, right? So NaCl solution that you have here in this it is given 20% of mass is given here. And in this NaCl solution, current passes through. And what is that current? 25 ampere. 25 ampere. Current efficiency is given, that is 62% current efficiency. Pass through 20 liter of NaCl solution. For this solution, the volume is 20 liter. Write down the reaction taking place at anode and cathode. How long will it take to produce 1 kg of Cl2? What will be the molarity of the solution with respect to hydroxide ion? Assume no loss due to evaporation. Means there is no loss in volume, right? So what is the reaction at anode and cathode, right? So we have NaCl solution, right? Means NaCl plus water, it is present over there. Okay, so NaCl plus water means we have Na plus, Cl minus, H plus and OH minus. So obviously the reaction is, the possible reaction is at anode, Cl minus get oxidized and it converts into Cl2 plus 2 electron, 2 Cl minus. This is a reaction at anode. At cathode, what happens? Water molecule get reduced, H2O. H2O plus electron gives half of H2 and half of, so we'll write 2 H2O, 2 electron. So we'll write H2 gas evolves and hydroxide ion OH minus goes out. So these two are the reaction at cathode and anode. Okay, so first thing is done. That how long it will take, what I write on that reaction taking place at anode. How long it will take to produce 1 kg of Cl2, right? So what we can write, 1 kg of Cl2 is equals to, if I find out the number of moles, so 1000 gram divided by 71. So it will be 1 point something, so 1.3 around. Right, 1000, so 14.08 mole exactly will get. It's not 100, it's 1000. These many moles of Cl2 we have to produce. Correct, Cl2 gas. Okay, now for this Cl2 gas, we are providing this current, right? So mass M is equals to, we can write EIT by 96500. So M by E is the number of equivalents. So M by E we can write, just now we have discussed this. M by E is the number of equivalents, is IT by 96500. So M by E is the number of equivalents. So we can write number of moles into N factor of it is equals to IT by 96500. We need to find out time, right? Because it is how long it will take to produce 1 kg of Cl2. So T is equals to what we can write? Number of moles we have already, 14.08. N factor of this is 2 into 96500. divided by I. I value is, I is 25, but effective current is what? 25 and 60% of that, because it is 62% efficient. Okay. So now when you solve this, you'll get T is equals to 48.69 hour. This is the time. And you can convert this into second also if required. So you get a huge number in second. So this is the time required to produce 1 kg of Cl2. Now what will be the molarity of solution with respect to the hydroxide ion? Assume no loss, okay? So OH minus ion produce, you see here, 1 Cl2, 1 mole of Cl2 forms and 2 moles of OH minus ion. Means double, right? So the number of moles of Cl2 into 2 is the number of moles of hydroxide ion, right? Because in this reaction, 1 mole of Cl2 forms, but 2 moles of OH minus is forming, right? So what we can write here, number of moles of OH minus is twice of to that of NCl2. That is 28.16 mole, right? 28.16. So molarity is what? Number of mole by volume of solution in liter. So 28.16 divided by the volume is given 20 liter, right? So this divided by 20. So it is 1.40 molar solution we get. So the answer for this question, you see, the first answer is this, the reaction at anode and cathode. The second answer is this, how long it will take to produce 1 kg of chlorine. And third answer is this, the molarity of the solution is 1.4 molar. Okay, so this is the fifth one that we have discussed. Okay, I hope you have understood this. It's just the basic concepts of equivalence, equivalent mass and all, so that we can convert those mass into number of equivalents, then equivalents into moles, etc. Okay, now the next one you see, for the galvanic cell, it is given AgCl solid, KCl 0.2 molar, KBr in AgBr solid, Ag. Okay, calculate the EMF generated and assign correct polarity to each electrode for the spontaneous process after taking into account in the cell reaction at 25 degrees Celsius. KSP is given, right? So E cell, what we can write, E cathode minus E anode. So first of all, you see, both side we have same electrode. So it is a concentration cell, okay? Concentration cell with different concentration of electrolyte. So it is electrolyte concentration cell, okay? So for concentration cell, it is a concentration cell. And for concentration cell, we know E naught of the cell is 0. So if you apply Nernst equation, E cell is equals to minus 0.0591 by N value is what? Ag to Ag plus to Ag, right? 1 log of concentration of product by reactant. Okay, so what we can write? We can write Ag plus on the anode side divided by Ag plus on cathode. Okay. We need to find out the EMF, E cell, means the concentration of Ag plus at anode and cathode we need to put, right? Fine. So for this, we can use the expression of KSP. KSP of AgCl is equals to, just a second, guys. Concentration of Ag plus KSP of AgCl is concentration of Ag plus and Cl minus. So we can substitute Ag plus from KSP of AgCl, and we can substitute concentration of Ag plus from AgBr. Correct? So here the expression we get is minus sign I'll take here, 0.0591 log of Ag plus at cathode, means on the right side, right? Cathode means AgBr. So Ag plus concentration is, we have 3.3 into 10 to the power minus 13 divided by the concentration of Br minus, right, into concentration of Cl minus divided by 2.8 10 to the power minus 10. Okay. Now this Br minus concentration we know, which is 0.001, and Cl minus concentration we know, which is 0.2. When you substitute all this here, you'll get E cell. And E cell is equals to, when you solve this, you'll get minus 0.0371. Negative value we get here, right? So as the cell potential is negative, right? Cell react potential is negative. It means the cell reaction is non-spontaneous. Is non-spontaneous, right? Hence, what is the correct cell? It should be other way, right? Means the anode here must be cathode, and cathode must be anode, right? So the correct cell is Ag solid to AgBr in KBr with some concentration, salt bridge, then KCl, some concentration with AgCl, phase boundary, Ag, and this is the cell reaction. Means Ag to AgCl, this part should be the cathode and this part should be the anode, then E cell will be positive. That's what the question is. For to assign correct polarity to each electrode. Polarity means what? What should be the charge on the electrode, positive or negative? Means if you find out whether it is anode or cathode, you can see the charge on it, right? Okay, fine. Next question you see. The standard reduction potential for half cell okay. The standard reduction potential for the half cell reaction, which is given here, is given 0.78, right? So this is the half cell reaction and its standard reduction potential given. Calculate the reduction potential in 8 molar H plus. What will be the reduction potential of the half cell in neutral solution? Assume all species at unit concentration. Okay. The standard reduction potential for the half cell is given. Okay, so H plus is present in the solution, right? H plus is present in the solution. So here what happens, E cell of this reaction is equals to E naught cell minus 0.0591 by 2 log of 1 by H plus square. Okay, so E naught cell is given 0.78 minus 0.0591 by 2 log of H plus square is 8, right? So 8 to the power minus 2 we can write. Further it becomes 0.78 plus 0.0591 into 3 log 2, right? So you can solve this, you'll get E cell, which is 0.833 volt you get. So reduction potential is 0.833 volt. The first result is this. What will be the reduction potential of half cell in a neutral solution? It's a very simple one. If the solution is neutral, right? For neutral solution, we can say H plus concentration is 10 to the power minus 7, assuming the temperature is 25 degrees Celsius only, because it is not mentioned here, right? Now we'll substitute this H plus here. So what we get, E cell is equals to 0.78 plus 0.0591 into 7. sorry, -7 into -7. So now when you solve this, you'll get 0.367 volt of cell potential, correct? So this is the answer for this question, 0.833 and 0.367. Okay. Next one you see, the chromium metal can be plated out from an acidic solution containing CrO3 according to the following reaction, which is this. Calculate the mass of chromium plated out by 24,000 coulomb. How long it will take to plate out 1.5 gram of chromium using 12.5 ampere current. Okay. So you see this reaction, first of all, it is CrO3 plus 6H plus 6 electrons this is the reaction we have, right? So 6 moles of electron it is taking, right? 6 moles of electron means the charge required here, is, according to this equation, we can say the charge is 6 Faraday. That is 6 into 96500 coulomb. This coulomb of charge gives 1 mole of chromium. That is what it is, right? The reaction is already balanced, you see. 1 mole of chromium. So which is 52 gram, right? This is 52 gram, right? 1 mole is this. So we can say if 6 into 96500 coulomb gives 52 gram of Cr chromium, then 1 gives 6 into 96500, and then 24,000 coulomb. This gives into 24,000. Okay, so that is 2.15 gram approximately. So the first answer is this. Calculate the mass of chromium plated out by this. This is the first answer. How long will it take to plate out 1.5 gram of copper using 12.5 ampere of current? Okay, so now you see, again we use Faraday's law of electrolysis. So M is equals to, we have EIT by 96500. Okay, EIT by 96500. We need to find out time, right? T. And mass is given, right? Mass is given, that is 1.5 gram. So we can say T is equals to 965, just cross multiply this, into mass is given 1.5 divided by E into current is 12.5 ampere. Okay. Now, what is this E? Since the N factor is 6, atomic mass is 52. So E is what? E we can write, I'll just write down here only. E is the given mass divided by the N factor, that is 52 by 6. So T is equals to, when you solve this, you'll get 22.27 minute approximately. Okay, so this is the second answer of this question. The second question. Okay, so this is it for this question. So guys, you must be feeling that the calculation is a bit difficult here, right? But you don't have to worry much about it, because these are the previous year question, 90s day questions we have. There we have subjective questions, so they give this kind of calculative questions. Okay, so the point is you need to focus on the understanding of concept. What is the concept we have? How do we solve those kind of questions? Okay, just focus on that. Okay, calculation will be easier for you. Okay, so this is it. We have discussed these questions today. Okay, we'll see you in the next session. Thank you.